In this episode of Earth is Our Home, Dr. Thomas Blaine will be looking at the Coriolis Effect. So stay tuned. Welcome back to another episode of Earth is Our Home with Associate Professor Dr. Thomas Blaine with the Ohio State University Extension Program. Tom, it's always a pleasure talking with you.
It's a pleasure being on here with you, Patrick. I enjoy doing these videos. It's something I've been teaching for a quarter century now, and I always look forward to each episode.
Well, you sort of threw me for a loop when you said that part 10, we were going to be discussing the Coriolis effect. Now, I'll be quite honest with you. I've heard that word several times, but I'm just not sure what it means.
Well, we're going to clear that up. We're going to take care of that. Sometimes people call it the Coriolis Force. You may have heard that term. People want to use that term. They can use it, but Coriolis is not a force. Gravity's a force. Okay. Electromagnetism, that's a force. But Coriolis is not a force. It's an effect of the rotation of the Earth on objects that move through the atmosphere, including air, which means wind flow and direction. It has a huge impact on especially our weather and climate. And it's a fun thing to talk about. It's the way that air and water spin the Earth's rotation. And you've probably heard the kind of myth, water spins down a drain counterclockwise in the northern hemisphere and clockwise in the southern hemisphere.
Yes, I've heard of that.
You've heard that.
Yes.
And that would be because of the Coriolis effect. Now, it's not true. That's not true. The Coriolis doesn't affect that way. And because those kinds of things are on a very small scale, Coriolis cannot operate on the scale of a sink, just like the tides can't act on your bathtub. It's not subject to tides, even though it's water. A body of water like the ocean is subject to tides. But it's fun about the Coriolis effect. I remember when I first went to the southern hemisphere, I tried that out. It doesn't work like that. But that myth that you hear about the spinning water down the drain in the two directions is a myth. However, on a large scale, the scale of circulation around storms, for example, that is governed completely by the Coriolis effect, as we'll see. The series is Earth is Our Home. And so far in the series, we focused on Earth's climate. We have gone through a history of climate change on planet Earth over the past 600 million years. We've discussed eras in which where we are in Ohio now was a hot house with conditions like you would find in Central America or the Amazon, very hot, humid. We've gone to eras in which the climate here has been frozen solid, the Ice Age, actually been ice ages. And we've talked about what phenomena have brought these hot spells on, what phenomena caused Earth to cool, to go into ice ages. We've talked a lot about these, and those are on the previous episodes that I would encourage you to go back and watch. So we focused on Earth's climate history. We've talked a lot about El Nino, La Nina, and things like that. And so today, this is the 10th episode in the series Earth is Our Home. And all 10 so far deal with Earth's climate or with phenomena that affect Earth's climate. So today I want to talk to you about the Coriolis effect, and we'll have to continue this next time too, because it's going to take a little bit of time to get through it, and I hope you enjoy it. Many of you have heard of the Coriolis effect. You've probably also heard the term Coriolis Force, that there's a Coriolis force. That's technically not accurate. Coriolis is not a force. It's an effect. So gravity's a force. You climb up a tree and jump out, you're going to hit the ground. And that's because gravity is a force that's acting on you. Electromagnetism is a force. Coriolis is not a force, but it's an effect. And it's an effect of the spin, the rotation of Earth, a rotating sphere in space. The spin of Earth has enormous effects for things that are moving through the atmosphere, including air. So it affects winds and wind patterns. We've done climate models on wind and why winds tend to blow in the direction that they do, both on a large scale, a macro scale, and on a small scale. But the Coriolis effect is one of the most important properties of any rotating object, like planet Earth. Now, the Coriolis effect causes winds in the northern hemisphere to swerve or bend to the right. That's correct, to the right. So it's not to the east or west, it's to the right. And we're going to show that. Winds in the southern hemisphere, because of the rotating Earth, tend to swerve to the left. Okay, so let's go back and look at Earth's climate engine. Let's take a look. First of all, we live inside a ferrule cell. So if you go up and look between the Hadley cell in the northern hemisphere, which is essentially a tropical cell of air, and again, we've covered this in detail in several episodes. When the air that joins the Hadley cell and the ferrule cell gets so heavy because it's cold, it's been aloft for a long time, it's very cold, it's heavier air, it sinks down to the surface of planet Earth. Some of it goes back toward the equator, some of it goes north toward the pole. And notice the one that goes back toward the equator swerves to the west, and the one that's going north in the ferrule cell swerves to the east. But they're really doing the same thing. It looks like they're doing the opposite thing, but they're not. They're doing the same thing. Why? Because they're both swerving to the right. If you're at that 30 degrees and you're a packet of air and you move north, east is to your right. So you're being forced to swerve to the right. Notice the tendency in the ferrule cell is to just go north. But because Earth is spinning, all right, you move to the right, which is, in this case, you're moving toward the east. Those winds are called the prevailing westerlies because they come out of the west. All right. The other winds, those in the Hadley cell, go back toward the equator, and therefore they're moving south. but to the right of south is west. So they swerve to the west. That means they're coming out of the northeast. Those are northeasterly winds. Those are the trade winds. So we got the trade winds, the prevailing westerlies, and way up there in the polar cell, again, those winds moving south, they're going to swerve and come out of the east toward the west. They are called the polar easterlies. All right. So let's talk a little bit about that. Basically, here's the summary. All winds in the northern hemisphere are bent to the right. Now, we did the northern hemisphere. You can go back and verify for yourself that the winds in the southern hemisphere are bent to the left. And this is regardless of east or west. So we've looked at the winds in each cell. We talked about the polar easterlies, prevailing westerlies, the trade winds, and we followed the flow from whence the winds are coming. And, you know, we could do it for the cells in the southern hemisphere. Notice those in the southern hemisphere, the trade winds come out of the southeast. The prevailing westerlies are coming out of the northwest. And then you've got, or polar easterlies, also down there coming out of the east toward the west. Why does the Coriolis effect work the way it is? Well, look, the Earth is basically a rotating sphere. And the rate of the rotation of the Earth is the same everywhere. One rotation per day. It doesn't matter if you're in Ohio or if you're at the equator. The Earth rotates one full rotation in a day. Now, the Coriolis effect exists because the Earth is essentially a rotating sphere. The rate of rotation of the Earth is the same everywhere, no matter where you are, whether you're at Ohio, whether you're at the equator. It's one rotation per day. The Earth spins one time on its axis per day. But the circumference of the Earth, that is the distance around the Earth, is much greater at the equator than at other latitudes. The Earth gets kind of fat at the equator. It's 24,000 miles, it turns out, the circumference at the equator. And here in Ohio, it's nowhere near that. And as you get to the pole, it's just 1 point at the pole. If you went within just a few feet of the pole and wanted to, walk around the Earth, you could walk in a little circle and you've been on every longitude line that the Earth has. Okay, just a few feet. But the point is the rotational velocity at the equator, because it's so much further around, 24,000 miles, and it turns that in one day, that means the rotational velocity there is 1,000 miles an hour. All right, that's faster than anywhere else. And it decreases steadily as you head toward the poles where it's zero. I mean, if you're literally standing at the pole, you're not rotating. You're on the axis on which the Earth rotates. So at the pole itself, you're not spinning. As you step down from the pole and go down, circumference of the Earth grows. By the time you get to 60 degrees latitude, the rate of spin is about 500 miles an hour, because the circumference of the Earth is about half at 60 degrees latitude as it is at the equator. Here in Ohio, we're a little bit more than half. We're roughly in the neighborhood of about 18,000 miles, I believe, circumference. So we don't have as far to go in a daily rotation. Well, this plays a major role and causes some phenomena that look kind of strange, plays some kind of crazy tricks on things. And it makes it look like a force is acting, but it's not a force. So imagine you're standing in Minnesota and you want to throw a ball down toward Louisiana. Okay? Louisiana is due south of Minnesota. The rotational speed of the earth is greater in Louisiana where you're throwing the ball. But since the earth rotates from west to east, the ball will appear to veer to the right as it heads south and probably miss Louisiana and hit Texas. It veers off to the right. It makes it appear that a force has acted on the ball, but it's really just a property of the Earth's rotation and the fact that the speed of rotation is greater in the direction where you're throwing the ball. Now, if you throw the ball from Louisiana to Minnesota, you're throwing from a direction where the Earth is spinning fast to a direction where the Earth is spinning slow. All right. So since the ball is moving into an area of slower spin, it appears to move ahead of where it was heading initially. It tends to move out ahead of that, which means to the east. And that would be to the right. And maybe it would land in, say, Wisconsin. So because of the Coriolis effect, winds tend to blow clockwise around high pressure systems. Remember, a high pressure system, the air's pushing out. So once it pushes out and it bends to the right, that's going to be a clockwise flow around a high. In a low pressure system, the air is moving in. So if you're on that air and you move to the right, you're going to be feeling like you're moving in a counterclockwise around a low pressure system. Hurricanes are gigantic low pressure systems. So they rotate counterclockwise. Now, a lot of people ask, well, what's a typhoon and a tropical cyclone? They're the very same thing as a hurricane. There's no difference. The only difference is they go by different names depending on what ocean basin they're in. Now, I want to look at a typical weather map. This is a weather map you might see when you tune in to the weather. This is a configuration from February of 2011. You can see that it is, in fact, a winter configuration. All right. Based on what you know now, you should be able to look at this map and tell where the winds are blowing at various places. Okay. So if you look, there's a gigantic storm or low pressure system centered over Maine. That is called a Noreaster. And they're very common. That storm just moves right up the East Coast. If you look at the isobars, the changes in the pressure, they're very close there, very close to each other. That means there's very heavy winds. Okay. Now, what I want to do is go back and look at the map and see if we can tell where the wind directions are. All right. Based on what we've learned. Look at Ohio. Look at Ohio. Where's the wind? You can see there's isobars there. There's differences in pressure there. As you move to the west, you're getting high pressure. As you move to the east, you're getting low pressure. That means the winds in Ohio are coming out of the north. The winds in Ohio are coming out of the north because they rotate clockwise around the high. All right. And since we're to the east of the high, they're flowing down. Also, they go counterclockwise in around the low pressure system. So if you look out to the east of Maine, out over the ocean, the winds would be coming up from the south to the right of the low pressure. They'd be coming out of the south. It'd be very windy out there because those isobars are so close together. If you go north of the low, up into Canada, they'd be coming out of the east. Look in between the high pressure system over Lake Superior and the low pressure system over Maine. Very heavy winds coming out of the north. Why? Clockwise around the high. So that high over Lake Superior is sending winds down from Hudson Bay down toward the Great Lakes. And the low's reinforcing that because it's going counterclockwise in the same spot. And they're driving that cold front, those northerly winds between the high and the low up there at Lake Superior and Maine. They're driving that low pressure system down. So you got a northerly flow, and that flow extends beyond the front down into Ohio. Let's look at central Texas. The wind's blowing out of the south in central Texas. Not real windy. The isobars are far apart. Not real windy, but there is a southerly flow. You got pretty mild conditions in Texas, where, especially central and east Texas, where the wind's flowing up off the Gulf because it's counterclockwise. If you look at New Mexico, the wind would be coming out of the east because, again, around the high that's up there in Utah and Colorado, the wind is blowing down and then it goes back around clockwise. So in New Mexico, it's flowing from east to west. The low pressure is directing it in that same direction from east to west. So they're reinforcing each other. So you can tell which way the winds blow based on the location of high and low pressure. And there's the summary that if you want to go ahead and pause this and look at that summary and then go back and look at the weather map, you can do that. Now, the next time, what we're going to do is we're going to look at some other storm patterns and how the flows around these storm patterns are influenced by the Coriolis effect. And we're actually going to look at hurricanes. Hurricane's a giant storm, like you saw that Noreaster, giant low pressure system. Well, that's a winter storm. A hurricane is a tropical storm. It's a warm weather storm, but it's also a giant low pressure system. And we'll also answer the question. It's a fun question. You know, since they got this low pressure that is counterclockwise here and it's clockwise in the southern hemisphere, does the Coriolis effect really cause water to flow clockwise down the drain in the opposite direction in the southern hemisphere, as opposed to counterclockwise in the northern hemisphere? So we'll have a little bit of fun with that.
The one line that starts in Arkansas and ends with the low pressure in Maine, notice all the little arrow brackets that you have on those lines.
Those designate that's a cold front, and the air out ahead of that front is more humid than the air behind the front. It's the humidity that distinguishes. But when you have a low pressure system, like in Maine, it generates a front. It doesn't just sit and spin. It generates this gigantic front. So if you followed the one off the coast of California and went way up there out of sight past British Columbia, there would be a low anchored up there too. And you can see going down through there, you've got the blue line with the arrows. So the blue line is a cold front and it's defined by humidity. So it's humid air out ahead of that one front, like in Georgia and Florida. In between, like Tennessee and Michigan, it's cooler, drier air. But behind the next one, it's even less humid. It's incredibly dry, very strong. But the arrows show, and the blue and the arrows show this is a cold front that is on the move. Whereas if you look at the red on the one up there in, let's say those other, remember I told you how the air to the right of the low in Maine was coming up out of the south? The air to the right in Maine is coming up out of the, notice that's red and it's got a circle. That's because that's a warm front, because it's coming up out of the south. Remember, I told you the air spins counterclockwise around a low. So the air to the left of the low pressure system is going south. In other words, the air over, that part of Canada above New York State and Vermont, it's pushing south. But the air to the right of the low, it's a big spin. It's spinning. It's spinning because of the Coriolis effect. And so that air out in the Atlantic Ocean is coming up out of the south. So the red is the warm front, if that makes sense. So you got warm air coming to the right of the low pressure system. And when you get to that line, boom, the air loses humidity. It gets up there where it's much colder. And that is basically a warm front. And if you notice out to the left, to the west of the high pressure system over Lake Superior, you've got red interspersed with blue. If you can see that, Patrick. And that means that front is essentially stationary right now. The front out there, it's not really moving. It's got some blue and it's got some red, and that's a stationary front. So those are fronts.
I know that we are looking at climate change and we're looking at global warming, but I think you're pointing out that our weather is a constant movement.
Well, it's true. Basically weather patterns follow the same kind of pattern. Like if you look at this pattern, this could be any February. This happens. This is from 2011. This is 10 years old. But the pattern we see with the highs, with the low, the Noreaster is a very common phenomenon in the winter. This configuration, a giant storm hitting the West Coast in the rainy season, which is winter. We see these patterns, and these patterns continue. But if you remember, one of the things we did talk about in one of our shows is that, for example, as you add energy to the system, there are a lot of meteorologists and climatologists who believe that even though these same patterns will continue to see these same kind of patterns, that some of the extremes of them may get more severe. In other words, we're adding energy to the system. We'll still see these same patterns. You'll see this next winter, I guarantee you'll see a pattern like this, and the winter after, and so forth. But I want people to understand how the climate engine works and how weather patterns form and everything like that. And then as we go, we will talk about what kind of changes global warming will introduce. I want to thank you very much for today, Patrick. I enjoyed going over the Coriolis